right, welcome back for week 2. So where were we last time? We got to this point where we had defined our 3 basic quantities that we're going to be studying: entropy, mutual information, and divergence. We then got through conditional versions of these, defining those. We went through the properties of conditional mutual information, conditional divergence, and finally we just need to see these properties for the conditional entropy. And we ended with me writing these out and saying we're going to prove them. So let's quickly do that proof. So we are trying to prove that if x and y are discrete random variables, discrete just to make our lives easy so that we're not having to worry about infinite things, they're taking values in some set x. We write mod x for the number of elements in x. Then the entropy is bounded above by log x, where the upper bound is attained if and only if x is uniform. The lower bound is attained if and only if x is constant. We have that the conditional entropy lies between 0 and the unconditional entropy, with equality if and only if x and y are independent on the upper bound. And on the lower bound, the conditional entropy is 0 if and only if x can be written as some function of y. There exists a function f such that for every state of the world, every outcome, this random variable is a function of this random variable. So I can take this random variable, do something to it, and get this one. The chain rule, that the entropy of a sequence, so some big vector, can be written in terms of the sum of the conditional entropies of each term. And this is then bounded by the sum of the entropies. Then if I have a function f taking x to y, then the entropy of a function of x is less than or equal to the entropy of x. So you never gain information. This is the data processing inequality, now written in terms of entropy. And there's equality if and only if f is injective, or 1 to 1. 5, if x and y are IID, then the probability that x equals y is at least 2 to the minus entropy, with equality if and only if x is uniformly distributed. Of course, because they're IID, if x is uniform, so is y. And finally, if we think of the entropy in terms of the distribution, it's concave as a map. So if I take a convex combination of p's, then I'm going to be increasing the value of h. That's the idea. So let's do the proof. We'll keep going on this board for now. Okay, so the lower bound is just the definition of entropy. You notice that p log p, well, p is less than 1. Log p is therefore less than 0. P log p is less than 0. Minus p log p is more than 0. So when you add them together, you get the entropy, which is at least 0. Easy. Okay, so lower bound as p log p is less than or equal to 0 for p in 0 to 1. Remembering that if I put 0 in, by definition, we put a 0 here. Okay, the upper bound, and let's take q. Qx equals 1 over the size of x, and apply Gibbs inequality. That's it. Okay. So from Gibbs inequality, we get the inequality. We also get equality if and only if p equals q, which is precisely this. And yeah, to show that the lower bound is attained, so we've got the lower bound, we've got the upper bound. Gibbs inequality gives us the if and only if here. For the lower bound, you notice that, well, hang on, the only way for these terms to be 0 is for the probability to be either 0 or 1. Those are the only ways you can get a 0 here. So if you're going to add up a bunch of non-negative things and get 0, every term in that must have p either being 0 or 1. but I've got a probability, so it adds up to 1. So there must be exactly one term, which is 1, and all the other terms are 0. So the probabilities of all my events, they're all 0 or 1, so exactly one of them is 1, and all the others are 0, which means it's a constant. Done. Okay, now that's point 1. Point 2. We know that 0 is bounded by the information. So we already proved this using a variant of Gibbs inequality. But we can write the information as h of x minus h of x given y. And we look at that for a moment and you rearrange it and you say that shows that the entropy must be bigger than the conditional entropy. Done. The upper bound is attained if they're independent. If they're independent, this is 0. Okay. The lower bound, we need to see, so for the lower bound, okay. So, sorry, I should say, if they're independent, this is just the entropy of x. So I get a 0 here. I get the lower bound in the information. But then when I look at point 2 here, I get that the right-hand bound is attained. There we are. For the lower bound, what do we need to do? We just write out again. We observe that h of x given y is equal to the sum over x's of probability of x times h of y given x equals x. So this is the conditional entropy. This is the entropy of y on this particular event, so conditioned with this particular value of x. So we could now, if we want, we can write this out as px p of x times the sum over y, p y given x log p y given x. And then basically the lower bound follows from the previous argument we had. So if you're going to get a 0 here, for this to be 0, all of these terms have to be 0 because they're non-negative. Okay, multiplied by probabilities, all these terms are non-negative, so every one of them has to be 0. So we get that the conditional distribution is trivial again. So there is a trivial relationship between x and y. So condition on the value of x, y takes exactly one value, which, if I've written it the right way, no, yes, I've been a fool. Okay, to save me pain, I'm changing it here. You can do the switch in your head. Okay, so we, yeah, just me being foolish. We get through here, and what we see is that for this to be 0, every one of these terms has to be 0. If every one of these terms is 0, then given the value of x, there's only one value of y that is possible. If I just consider the function that takes me from that value of x to that value of y, there's my function f, proving the result. Now, of course, we don't need to worry, because we're in discrete spaces, we don't need to worry about any regularity of that function. It's just a map from a discrete space to a discrete space. So every map is sensible. If we were trying to do this in a continuous space, we'd be a little bit more worried about making sure that map has some nice properties like continuity, for example. Point 3. So if we go back to the previous theorem on the mutual information, it's basically just the mutual information proof of point 3. Okay, so from properties of mutual information, what do we see? Well, when we go back, we have the information chain rule, and we basically can just rearrange the information chain rule into the entropy chain rule because the two can be switched around between each other. Finally, and to get, so that gets you from here to here, just by rearranging in terms of information. To get from here to here, well, we've already just seen an inequality here between x and y. So I'm just going to apply that where this thing is y and this thing is x, and each term must be bounded by the corresponding term here. So all I'm doing is I'm saying, well, generically I can drop the thing I'm conditioning on and just get a worse bound. So I'm going to drop whatever I'm conditioning on in each term here, and I'll get a worse bound, which is the sum of the entropies. Done. And to get equality, I just need independence. So to get independence comes from, well, the entropy being 0 if and only if you have independence. Point 4. I'm trying to get through these quickly so we can get on to more fun stuff. We can write the entropy of x and f of x. That's equal to, well, let's expand this thing. It's the entropy of x plus the entropy of f of x given x. But given x, I know the value of f of x. There's no uncertainty left in its distribution. So I'm in the case of point 2 here. So I get that this is just h of x. And I can do another decomposition. So, sorry. So let's split this up the other way. This is equal to h of f of x plus h of x given f of x. Okay. Well, in general, I can't say much about this. If f lost a lot of information, let's say f was a trivial map that always returned 0, you can't say much about x from it, so this would not be that interesting. But on the other hand, I can tell you that this is positive. So I know this is at least as big as h of f of x. So just by the fact that this is positive, I know that this term is bigger than this. This line is equal to this line, so h of x is at least as big as h of f of x. When are they the same? Well, they would be the same if this term was 0. And when is this 0? It's when knowing the value of f of x tells you the value of x, which is essentially when f is injective, when it has an inverse on its range. Okay, point 5. Point 5 is Jensen's inequality. Okay, so how is it Jensen's inequality? Well, I can write out 2 to the minus h of x. This is just, let's write it out in full. In terms of random variables, this is 2 to the power of the expected value of log p x. Now, 2 to a power, that's a function that looks like this. It's convex. Therefore, I know this is less than or equal to the expected value of 2 to the log p of x. So this here is Jensen's inequality. Okay, but now I know my logs are always to base 2 to the power, so those cancel down. This is just the expected value of p of x, which is equal to the sum over x's of the probability of x times the probability of x. So it's the probability squared each term. But if you think about it, this is the probability that x equals y if x and y are independent. So this is the probability x equals y. X and y are IID. So if they're IID, what's the chance that they are the same and the value little x? Well, here's the chance that x is the value little x. Here's the chance that y is the value little x. So this is the chance that they are both the value little x. I add this up over all possible outcomes, so I get the probability that they're the same. So I get this probability coming out.
I got a question regarding the fourth.
Fourth one, yes.
So suppose some of the probability probabilities are 0.
Yep.
If there the function f is not injected, I guess we'll also get equality.
Yeah, so this is why I said injective, not that it admits an inverse. So it doesn't have to be a bijection.
It might be not inject on the values where probability is 0.
Okay, so we can restrict it to the set of outcomes with positive probability, and then we're fine. Absolutely. So here, because we're in discrete spaces, we can often drop zero probability things, and it all makes sense. And so we do that just because otherwise you end up writing very, very painful statements. It's injective, except possibly on the set where things are zero, and it takes longer to write. Any other questions? Good, okay. And finally, 6. We say g of x, if I write g of x is minus x log x, this is concave. And I'm just adding things like this together, and the sum of concave functions is a concave function. So when I write out the sum over, I apply this to each of the terms in the probability and add them together, that's now a sum of concave functions. All right, so there's these properties. Okay. So that's almost everything we need to know about entropy, but there's one inequality that we haven't seen yet, which is quite cute and will prove useful. And this is Fano's inequality. Okay, so the idea here is one situation we often come up with is we're trying to estimate a random variable. We have a random variable, we're trying to estimate it using something else. Okay, so we have a variable y that we can see, we know the value of, and there's a variable x we don't know the value of, and we're going to try and use y as an estimate of x. So we want to maximize the probability that they are the same. Well, Fano's inequality is if x and y are discrete random variables in x, then if I look at the conditional entropy of x given y, this is bounded above by the entropy of the indicator function of x is not equal to y, plus the probability that x is not equal to y times the log of psi, the log of the space, minus 1. Okay, so what's this telling me? It's trying to tell me that there's a few ways of looking at it. One is if you rearrange this, you can rearrange this to give you a lower bound on the probability here. So you know if there's entropy, there's a limit to how good your estimate can be. So if I rearrange this, take this over to this side, divide by the log of this is going to be big enough to make it interesting. If I do that, then I get a lower bound on the probability, which says if there's still entropy between them, there's no way that I could estimate x accurately from y. Well, it gives me a lower bound on how accurate that estimation can be. Okay, so let's see the proof. To save me writing, z's the indicator of x not equal to y. So of course this is the random variable, which is 1 if x is not equal to y and 0 if x equals y. So this is still a random variable. I don't know it. There we are. Then observe that the entropy of z given x and y is 0. It is a function of x and y. In fact, I've written the function down. So the entropy is clearly 0. So then, the entropy of x given y is equal to, well, let's expand, x given y plus h of z given x and y. Here I'm just adding 0. Pointless thing to do, but I can do it. Okay, so this is then, well, hang on, I can put this together using the chain rule. This is the entropy of the pair xz given y, which is equal to the entropy of z given y plus the entropy of x given y and z. So far I've just used my chain rule multiple times to rearrange this to get a different expression for this entropy. But now I'm going to bound this. I'm going to say, well, this term is bounded above by the entropy of z, and this term is, well, I'll just leave it as it is, x given y and z. Okay, once I have this, last step, I'm going to write this out as the entropy of z plus the sum. I'm going to expand it along y. So this is the sum over y's of the probability y equals y, z equals 0, entropy of x given y equals y, z equals 0. So these are the 0 terms for z, and then I've got to add on the non-zero terms. So plus the probability y equals y, z equals 1, times the entropy of x given y equals y, z equals 1. Okay, so that's just expanding everything out in terms of these conditional entropies. But if I know that y equals y and z equals 0 implies x equals y equals y. If z's 0, then x and y are the same. I know the value of y, so now I know the value of x. Easy enough. So the entropy of x given y equals y and z equals 0 is 0. No entropy there. Otherwise, y equals y, z equals 1 implies x is not equal to y, because there is an error. Y is y, so the one thing x can't be is y. Okay, which leaves, so the size of x minus 1 alternatives. Therefore, if I look at the entropy of x given y equals y, z equals 1, that has to be, well, it's some distribution over size of x minus 1 elements. I know that the entropy is going to be bounded by log of the size of x minus 1. Okay, so it follows that, so let's substitute this calculation and this calculation in. I get that h of x given y is less than or equal to h of z plus the sum over y's of the probability y equals y, z equals 1, h x given y equals y, z equals 1, which is less than or equal to h of z plus the probability z equals 1 times log size of x minus 1. And we're done. So this is Fano's inequality. So this is just the same thing that we wrote up there, just written in terms of z's. But the point is to try and say entropy really does give us something. The fact that there is entropy means there is no way for us to do magic. There's no way for us to estimate x from y if there's an entropy bound here. So this entropy tells us that there has to be some bound on the probability of error coming out of this type of a problem. Corollary, just so that we've got it, h of x given y is less than or equal to 1 plus the probability x not equal to y log size of x minus 1. Here I'm just using that z takes two values, so I have a bound on the entropy. Okay, so that is everything we're going to know about, or everything we're going to use at this stage about entropy in general, which means, at last, oh, yes?
Where do we achieve equality in product?
When do we achieve equality? Okay, so we achieve, if we look through the calculation we did, we have a bound here, which is, so 1, and a bound here. So when do we get equality here? It's when the chance of an error doesn't depend on y. And here, it's when the distribution of x is uniform given there's an error and a y. So basically, it's a conditional uniformity type statement. So it's not quite that x and y are independent and uniform, but it's sort of close. Happy? Sorry, I can't give you a better answer than that. Okay. So why did we bother doing this? Well, one point of doing this is so we could understand codes. And so the next thing we're going to try and do is we're going to try and explain what do we mean by a code. So what we're thinking, we have a message, for example, a sequence of characters written in the Latin alphabet. Or, given the last few years, we have a sequence of text through which we run to tokenize it. So tokenization is the thing you do before you build a large language model, where you take your long text or whatever object you have, you try and build little chunks of it, often words or pieces of words, and then you work at the level of words. And so those are the elements of your language. Okay? In this course, we're going to be focusing on doing things at the level of individual characters, because I don't want to be doing something which is going to take months to train. If I do it at the level of characters, we'll still see enough to get a bit of a feel for what's going on, but I'll be able to do it on my laptop. Okay, so we have an input alphabet x, okay, and we want to store it, a message, in terms of an alphabet y. Usually y equals 0, 1. Okay, so what I've got is my input thing that I'm trying to work out. I'm then trying to encode this in terms of a sequence of zeros and ones, and I want to do that efficiently. So definition. So for a finite set, so when I say alphabet, all I mean here is a finite set. That's all I'm trying to say. Denote, so finite set x, denote by x star the set of finite sequences aka strings in x. Okay, so if my alphabet is the Latin alphabet, then an example of a string would be the word denote. It is a finite length sequence of characters. Okay, for x equals x1, x2, up to xn. I'm not going to write a symbol for concatenation. I'm just going to write them next to each other, okay, rather than putting any symbols in between them. Okay, so this is in x star. It's a finite sequence taken from x. Okay, with xi is in x. We say the size of x equals n is the length of the string. Okay. So given two finite sets, x and y, we call a function c which maps x to y star a symbol code fixed to variable length. I only say this because we will later see variable to fixed codes. The idea being I'm going to take one input and take it to some string of some length. And I'm not saying how long that string has to be. Okay, so I've got a symbol code and call c of x, which is now in y star, the code word of x in x. Y is said to be d-array if y, the size of y is equal to d. And as I said, typically we will be working with the size of y being 2. Okay, so now we have a definition of what we mean by a code. We can try and work with this. So let's do a little example. And we'll see where this can get unstuck. So let's take my input set being 1, 2, up to 6. And c of x, the binary expansion. Okay, so it's got a binary expansion, i.e. code words. Let's write them out. 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 2, 3, 4, 5, 1, 1, 0, 6. There we are. There's my code words that I'm thinking about. Okay, so this seems like it should work. Every input has a distinct output. Seems good. The problem is, okay, this does not allow us to recover the original sequence of input, e.g. 1, 1, 0 can come from, well, we could just get x equals 6, or I'm going to be using this on sequences, and this could come by x equals 1, 2. Because if I send a 1, then a 2, I will send exactly the same message. And that's the problem that we're trying to solve. So we're trying to look at how do I get something which when I transmit a sequence of characters, I'm still going to be able to figure out what I originally said. Okay, so we need to get a little bit more definition so that we can make this rigorous. So definition. Let C, which maps x to y star, be a symbol code. We denote by C star the extension of C to X star by concatenation. What do I mean? C star of x1, x2, up to xn is just going to be the concatenation of the resulting messages. C star of, well, it's C of x1, C of x2, all the way to C of xn. And the point is, I don't have commas here. This is not a vector. This is just one concatenated string. Here it would be perfectly fine. If there was a comma here, I'd be perfectly happy. I'd know this is a 1 and this is a 1, 0. But in general, storing a comma is another thing I have to remember. I would much rather not store the comma and just store 1, 1, 0. Okay. So we say C is, so 3 options, unambiguous, if C is injective. Okay, so here this is unambiguous. C is injective. Every input has a distinct output. Okay? But that's only at the level of C. It's only at the level of what happens to a single input. Okay? So each x in x has a different C of x. So that's an unambiguous code. A better or stronger statement is a uniquely decodable code. We say it's uniquely decodable if C star is injective. So now every sequence of characters maps to a different sequence in Y. Okay? So each x in x star, so every sequence maps to a different C star of x. Okay, so there's a different long sequence. This code here is not uniquely decodable. There's a third class which is quite nice, which is we call a prefix code. Which is a stupid name, but it's standard, because when I say a prefix code, I mean a code where you don't have prefixes. Okay, so what's a prefix code? A prefix code is where no code word C of x for x in x is a prefix of another code word. Okay, i.e. there does not exist x or x1, x2 with C of x1 y equals cx2 for some y in y star. So what's so nice about prefix codes? Well, when you've got a prefix code, you take your message, you go along the message, and once you've found something which is a code word, you know you can stop. Because it's not going to be, you're not going to get another code word coming after which starts with this. So you go along, and once you've got a code word, you say, right, I can decode that, and now I start again. So prefix codes are great. Unambiguous codes are a bit useless. Uniquely decodable codes sound good, but they're a nightmare to work with. So clearly, we know that prefix codes are a subset of unambiguous codes, which are a subset of, wrong place, uniquely decodable codes, which are a subset of unambiguous codes. But our interest is going to be mainly down this side of the board. So uniquely decodable sounds good. Sounds like what we'd really want. Maybe we can do better. The problem is they can be an absolute nightmare to work with. So here's a little example. So example, x is equal to the set A, B, C, D. Y is my favorite set, 0 and 1. I'm going to say C of A equals 0, C of B equals 0, 1, C of C equals 0, 1, 1, and C of D equals 1, 1, 1. I claim this is a uniquely decodable code. It's clearly not prefix, because 0 is the prefix of 0, 1. But I claim it's uniquely decodable. I claim this partly because if you look at it backwards, it becomes a prefix code, read the other way. But it leads to fun. So if I give you the string 0, 1, 1, 1, 1, 1, 0, 1, what could encode to that? So what message encodes to this string using this rule? This one here? CBD? I don't think. No. So I think, okay, if we look at this backwards, we get at the end we have a B, then I go back, so I get a D, and then I get a C. Okay, but what if I changed this just a little bit, and I said 0, 1, 1, 1, 1, 1, 1, 1? What sends that message? Okay, so because I told you it's prefix if I go backwards, so we can actually decode this, those three have to be a D. Then I get these three are also a D, and this is a B. And you see why this is a bit of a pain, because something that happens quite a bit later has changed how we interpret the beginning. So in terms of actually doing decoding, it's not so fun. Particularly if I'm going to get a stream of data coming in and I'd like to decode it on the fly. Okay, so it might be that uniquely decodable is the right set, but it's going to turn out there's a beautiful result that says essentially we don't need to care about uniquely decodable codes. There's no advantage to going to uniquely decodable over prefix. And this is the Kraft-McMillan theorem. So Kraft-McMillan, Kraft proved a version of this result. He only talked about prefix codes. And then what McMillan did is he showed that this applied to uniquely decodable codes, which among other things proves that uniquely decodable codes don't have any real advantages. So what's the theorem? It's two statements. First of all, let C, which maps X to Y star, be uniquely decodable. And write Lx being the length of C of X. So this is the length of the code word I get out of X. Then the sum over the x's. If I think about this, I must have size of y to the power of minus Lx is less than or equal to 1. So there's a universal bound on any uniquely decodable code. So any uniquely decodable code must satisfy this inequality. In particular, all the prefix codes also satisfy this inequality. Okay, point 2. Given Lx and y satisfying that inequality, there exists a prefix code C, which maps x to y star with the length of the code word being Lx for all x in x. So what does this tell me? If you give me anything uniquely decodable, it must satisfy this inequality. But also, if you give me any numbers satisfying this inequality, I can build a prefix code with those lengths. So there's really no advantage to looking at uniquely decodable codes, because if you come with your favorite uniquely decodable code, I'll say fine, and I'll return to you a prefix code with exactly the same code word lengths, but mine is prefix rather than uniquely decodable. Okay, we don't have time to go through the proof of this today, so we'll leave that for tomorrow. It's quite neat, and we'll work from there. So I'll see you then.